Today we're going to cover section 2.4, the cross product. What is the cross product? The cross product is when you have u and v, two vectors, we want something that is perpendicular to both of them. Okay, something that sticks, in other words, something in the third dimension. And to come up with that, we are going to derive it from the dot product. Now remember to by the definition of the dot product, one of the property is that when two vectors are perpendicular, called orthogonal, then their dot product is 0. So if we have two cross products, then what we need is something that a third vector where it dots the first two vectors and the result is 0 in both cases. So let me write that down. And so I wrote out our situation. We have u and v, those vectors are given. I wrote the underline here to indicate the boldface type in the book. Now anyway, so the underlined ones are vectors. And so we're given two vectors. We need to find the third vector, w. So these two are known, but this one is unknown. Now, and we need to find the vector w such that it is perpendicular to both u and v. So we apply the dot product principle. Okay, the dot product of perpendicular vectors are 0. And then we end up with two equations. And we're going to solve these two equations. We're not going to completely solve them because we have, remember, u and v are known, w is the unknown, but we have 3 variables and only two equations. We need 3 equations to solve them completely, but we don't need to solve them completely in the sense that we only need to know like what kind of proportion they are. That is, we don't care. We're only looking for something that's perpendicular. It doesn't matter how long it is. So we can do that with just 2 variables, as I demonstrate here. First, we have to do a bunch of multiplication, and then we'll multiply the top one by v3. Okay, multiply by v3, and then the bottom one by u3. Let's see. Let me not write the x here. So we'll do the multiplication and then we'll subtract it. And for the purpose of getting rid of the variable w3, so we have 1 equation left. And this is there's a name for this in simultaneous equations. So let's do that in our head. Actually, let's not do it in our heads. Let's just write this thing out. And so here it is. Then once I did the multiply by v3 on top, okay, and then u3 on the bottom across the board, you notice that the last term right here, they're the same. So if we subtract it, then we get 1 equation and without w3 in it, which I will write it out right here. Actually, I will just write it out this way. So this minus that, right? So w1 is being multiplied by u1v3 minus u3v1. And then this one is plus, that's w1. And then w2 is being multiplied by u2v3 minus u3v2. And that equals to 0. All right. Now at this point, you notice that there's w1 and w2. So if we let this thing equals to, let me see. Now if we let w1 equal to this part, okay, so this thing, we'll let it equal to w1. And this thing, we'll let it equal to negative w2. Now if we do that, then this equation will stand, right? I mean, you know, that becomes w1, negative w1, w2 plus w1, w2, that's 0. And therefore, that will be one of our solutions. That's not the only solution, but that we're only looking for one solution. So that's good enough. Therefore, we will set w1 equal to that, and I'll write it down. So I have it written down here. Now notice that your book answer has a negative sign here, and flip this around, which is the same thing, but I'm going to keep it this way for now because what happens is, so we have now w1 and w2. And what is w3 then? We can plug it back in here and come up with w3. or we can just look at the pattern. Okay, what is W3? W3 equals to 3. Okay, if you follow the pattern, that should equal to when, see, 1 goes to U2, 2 goes to U3, so 3 should go to U1, okay, and then times V, the one that's more than that, so it goes to V2, okay, and that is U2 goes to V3, so U1 goes to V2 minus, and then the one above it, which is U2, and then V1. And that, following the pattern, should be the answer. And is it? Yep, that is what the book says. The reason is because there is nothing different between W1 and W2, right? They're all symmetrical situation, so it should all work out the same. And that is our W. So our W is defined is a vector which is called the cross product, which is calculated by doing all this, a bunch of multiplication and subtraction, okay, which, as you can see, is somewhat painful, but that's the way with the cross product. The cross product is not as neat and clean as the dot product. And the difference is the cross product is a vector, okay, whereas the dot product is just a number because you multiply all the stuff out and there's no more direction left. But the cross product is still a vector because you end up with 3 numbers, which gives you a certain direction. Now, so let's look at the next page where on top, where your book wants you to check that this actually is orthogonal. Your book even says it never hurts to check. Oh yeah, I say it hurts me deeply to do all that grunt work. Look how much grunt work there is. So please do that as part of your homework. Check that U cross V is orthogonal to U on page 166. Now that way it doesn't hurt, at least it doesn't hurt me, right? And anyway, so once you've checked that it's orthogonal to U, it will be orthogonal to V because they're no different. One is the same as the other. And then you can prove that the cross product formula is indeed correct. And so with that, please do example 2.31 as part of your homework, where you follow this formula and calculate the cross product of some vectors. Now let's then go to the next page, 167, where we have to figure, there's a trick to remembering which way the cross product goes. Because if you have something that's perpendicular to 2 vectors, it can say the 2 vectors, let's say they're on the plane, right? So the third vector will, being the perpendicular to both, it has to stand straight up in the third dimension. Or it can go straight down. They're both orthogonal. Well, which one is it? What you do is, if it's U cross V, okay, then you put your hand out like this, and you line up your fingers along U, okay, and where the rest of your palm is lined up around V. So your finger swings from U to V like this, and then which way your thumb goes will be the way of the direction of the cross product. In this case, is up. Now, if you have to do it this way, your U is here, and you have to swing it like this, then your cross product is pointing the other direction. So, and that's how you remember which way the cross product goes. It's called the right-hand rule, all right? And then the next thing is, the way the cross product is defined, it has to subtract and stuff as it works out, and then the cross product is not, what do they call it? Commutative. That is, U cross V is not the same as V cross U, but it's similar though. It's just the other direction, okay? I mean, it actually equals to the negative. So to see that, please do example 2.32 as part of your homework. Next, let's look at the bottom of the following page, where it mentioned that what happens to the unit vectors I, J, and K if they cross themselves. Anytime things that cross yourself, you need something to be I cross I. Well, as it works out, that if something crosses itself, the way the math works out, it equals to 0. Okay, and so is J cross J and K cross K. That's just something you remember to simplify calculations. But there's more to it than that. Now let's look at the next page. And next page which tell you a bunch of stuff, which is I cross j equals to k. Okay, and you can do that with the right thumb rule. J cross k equal to I, k cross I equal to j, etc. And you can check it with your, well, you can just check some of it, I guess. And so on. There's all these things. Do you need to remember that? Not necessarily. You just figure that out as it just the unit vectors, when they cross themselves, they end up being a unit vector, and it's just that they will be a different one probably. Yeah, they have to be a different one. Anyway, so with that, please do example 2.33 as part of your homework. Next, let's look at the properties of the cross product on page 169. The properties are, first, the cross product is not commutable. That is, if you flip it around, if you think about v cross u instead of u cross v, you have to slap a negative sign on it. But otherwise, it is the same, except for the negative sign. And then the distributive property does apply, and so does adding some scalar vector. Next, we have when something crosses a 0, that's just that's 0. Okay, we'll just figure that is 0. And the cross product, something crossing itself, is also 0. And we will, and that might not be obvious, but that's just that will be obvious soon. Or I mean, that will be proven soon. And the last one, the quality, which is called the scalar triple product, is probably the most important one in this list, which says that when you have a dot and cross product together, you can rearrange it like this, and exactly this. Okay, that is u dot v cross w with v and w in parentheses. You can rewrite it as u cross v dot w. Now this matters. This exact thing has to be followed, being that the cross product is not commutative. You cannot just run it around. For example, this, if you say u dot v cross w, is that equal to that? No, this is not okay. Okay, this is not the same thing as that. So this is the only way it works. And so when you apply this theorem, then you have to pay very careful attention that everything fits exactly. The dot product, that is you can have the dot in front, okay, the cross product in parentheses, or you can move the cross product to front and then dot the last item. But that's all you can do. Do not, come up with something that looks similar but isn't identical, and none of that stuff is gonna work for you. Now the proofs of property 1 is all the proofs. You basically do the algebra and then see that it comes out. So let's see, proving property. Now for the proofs, you mostly just work on the definition and the algebra. For example, u cross v equals to negative v cross u, and after you write everything out and then realize, well, it is. Now from there, you can also tell that if something cross itself is 0, because u cross u is equal to negative u cross u. And anything that's equal to the negative of itself, it has to be 0. Okay, nothing else does that. So please do that as part of your homework. That's the proof of part 1. And next one, crossing some 0. Crossing a 0, then you have a bunch of zeros, right? Being that you're working with 0, then you multiply by a bunch of zeros and then subtract it, and you end up with 0. So that is fairly straightforward. Obvious if you think about it. And lastly, the scalar triple product is more complicated, but no harder. Then you do all the stuff, write every single thing out, and then eventually you realize that it equals to that other thing as claimed. So please do that as your homework as well, which is please prove properties, what is the other one? Properties 1 and 6 as part of your homework. So please do the next example, 2.34, as part of your homework. And we have come to theorem 2.7. what is the cross product? The magnitude has a very convenient and interesting formula. That is, u cross v is equal to the magnitude of u times magnitude of v times sine theta. As you remember, the dot product has something like that, except it was cosine theta. So between the two things, two formulas, you can figure out the magnitude of the different products. Of course, the magnitude only gives you how big it is. It doesn't tell you which way it's pointing. But it still helps a lot. Okay, so the proof of it, as you can see, is the brute force proof. That is, you dig out the formula, you're going to prove the squared form, okay? And then we'll take the square root later when everything's squared. And as you can see, you are going to have a lot of stuff. And in the middle, what you're doing here is in the middle, you will add even more terms right here. And add, I don't know what you're adding, but whatever it is, you're adding so that you can like doing something like sort of like completing a square, but not quite. But anyway, such that this equation shows up, and then eventually the answer will fall out. So please do this as part of your homework. Now, when I tell you to prove something that's already proven in the book, what I mean is that you need to look at the theorem, and then don't look at the answer and try to do it yourself. And if you're like, oh, I have no idea how to do it, then look at the first line, and see if that gives you a clue. If that still doesn't work, then look at one more line, and keep working on that until you're like, oh, okay, at least you know where you're supposed to go. Then you do that part and keep working your way down. And that is, you use the book's proof like the answer key, okay? And that way you practice doing the proving yourself, which is extremely beneficial in terms of being good at math, really. That makes the difference of the people who are good and people who are just barely struggling through. You just do some of the proofs and examples in the book is how you do it. So anyway, so then eventually we figure, so that gave us, what is it, the magnitude of u cross v. And with that, we can, what is that? Find the magnitude. Okay, next example, of course, calculate the magnitude of some cross product. Example 2.35, please do that as part of your homework. Next, let's talk about something called the determinant. The determinant is a way of, is a shorthand for expressing a bunch of multiplications and additions. The shortest determinant is the 2 by 2 one. Okay, you multiply it by crossing. That is, you write a cross. You draw a line from A1 to B2, and then from B1 to A2. So, and the determinant is calculated as A1 B2 minus B1 A2. Subtracting, you add down and then subtract backwards up, which that doesn't sound too bad until you flip the page. And that was just a 2 by 2. That's the smallest determinant you have. And then you're going to look at something called the 3 by 3 determinant. Okay, and that, you know what that means? That means you use A1 and then and calculate the determinant of whatever is down there. And then do A2 and calculate determinant of something else. And then the A3, calculate the determinant some more, which is a giant headache, okay? And I should mention that I don't like doing grunt work. And that is, the 3 by 3 determinant is when your head starts to hurt, but that's nothing. The determinants can be 4 by 4, 5 by 5, and it's a huge problem, except that we do have computers and calculators which can do this stuff really fast. But even then, even with a computer and calculator, I get too tired by just typing in those 9 numbers. Ugh. It's a total pain, because you can bet I'll mess up one of the numbers, so my entire determinant goes to pot, and yeah, it was not good. But anyway, so to do the determinant, you need to do a lot of math, and you need to not screw up on the way, like in any of it, because you mess up so much as once, you're dead in the water, so to speak. And so please do example 2.36 as part of your homework. So looking down at the book, here we have cross product expressed in terms of determinants. the purpose of this thing is to help you memorize the formula for U cross V. Now, does it help you memorize? I don't know. It probably helps some people. It doesn't help me. I don't bother memorizing the formula of the determinant. If I need it, I will look it up. And anyway, I took an entire course on vector algebra in college, talking about just this type of thing, and I don't think I did determinants very much. I avoid it if I can because it's a complete pain. Anyway, but it is extremely useful, so you need to know how it works. And and anyway, you probably already had it at some point, but we're just revisiting it briefly now, as I guess the book considered an easy way to remember the definition of the cross product. So having said that, please do example 2.38 as part of your homework, where you calculate the cross product of two random points. And 2.37 as well, I forgot to mention. And either way, you're just practicing using, applying the cross product formula, which is quite painful. So you should allow yourself more time to do this type of thing. It is important to do a little bit of it to get a feel of what the cross product is. So having said that, let's look at the area of a parallelogram on the following page, 174. Now, if you have, I have two vectors that are not, that forms the side of a parallelogram, okay, then the area of the parallelogram just happens to be the magnitude of the cross product. And the proof is also extremely straightforward. It's base times height. So I'll let you look at the proof more carefully. Well, yeah, actually the height is just the magnitude of V times cosine theta, okay? And I don't even need you to do it at home. Let's just look at it. The height is magnitude of V times sine theta, and then times the base, and that is your formula, which happens to be the magnitude of U cross V, because we already mentioned that U cross V equals to UV sine theta, in magnitude, of course. So that is the formula for area of a parallelogram. So next, example 2.39, when you're supposed to calculate the area of a triangle made by two vectors, I guess, or maybe three of them, who cares? The point is, you to calculate a triangle which half a parallelogram, then you use the area of parallelogram and then divide it by 2. So please do example 2.39 as part of your homework. Next, let's go to page 176, where we look at theorem 2.9 concerning a triple scalar product. What was the triple scalar product? It was U dot V cross W, which also equals to U cross V dot W, which I have written down right here, okay? Remember, don't mess up the triple scalar product. Now, that happens to be the same as the determinant of the 3 by 3 determinant, with U written on top, and then V written on the next line, and W written on the third line. That's just another way of saying the same thing, okay? And so we don't need to really prove that. That's just how it works out. But you can look at the proof a little bit if you want. There are a bunch of symbols, but they mean the same. It's just how it's done. The determinant is another way of saying it. It's not a shorthand really, because the determinant is a lot of work. So you're doing the exact same thing. So having said that, next example, please calculate the triple scalar product for something. Example 2.40 as your part of your homework. Next, if you work with the triple scalar product a little bit, then you might notice certain situations, such as there are certain identities that you can come up with, such as that one, and stuff get moved around, and they're extremely difficult to memorize. So I don't even think it's necessary to memorize them. It's just something. Are they useful? Well, I don't know, maybe not. But anyway, I want to mention it. So if you ever need and this thing, you know where to find it. So then let's look at the next thing, which is the volume of a parallelepiped. The right pronunciation is probably parallelepiped or something, but I'm just going to call it the parallelepiped. It just means something that's in the shape of a which is a 3D parallelogram, like this, okay? And in other words, you have a box, but it's slanted. Somebody pushed it over. So it's a slanted box, and it's formed by three vectors all lined up along one corner, u, v, and w. This is on the next page. Now, the volume of the parallelogram happens to be the triple scalar product, and the proof actually is quite nice. That is, if you look at the next page, page 178, you notice that the proof that the triple scalar product happens to be that is, first we know that the bottom area happens to be v cross w. That is, the cross product happens to be the area of something. Did we mention that? Let me check. Yes, we did mention it. Theorem 2.8 a few pages ago, which says that the cross product is the same magnitude, is same as the area of the parallelogram that the two vectors make. So therefore, the bottom area of this thing is w cross v, or v cross w. And then what is the height? The height is just the projection of u onto something, onto v cross w. Okay, that which is perpendicular to it, and therefore you multiply that stuff together, and it happens to be the scalar triple product, this triple scalar product. Now that's how you calculate, and this scalar triple product happens to be something you can use to calculate a parallelogram with. And so with that, please do such a calculation in example 2.41 as part of your homework. Next, let's look at example 2.42. Now, the example of 2.42 wants you to show that 3 points are coplanar. That is, there are 3 points, three vectors are coplanar. 3 points are always coplanar, so there's no point in showing it. To say 3 vectors are coplanar basically means those 3 points that the vector point to plus the origin, that is 4 points total, are on the same plane. And that's the hard part, okay? And so we have 3 vectors to be coplanar. And how are we going to show that? By showing by this neat trick, we're going to show the parallelogram, the 3D object formed by these 3 vectors, are 0. That is, the thing collapsed, okay? If it's 0, then the three vectors has to be on the same plane, because they can't create any volume for it because they're all flat. I mean, not flat, but well, they're all in 2D, right? Nothing is sticking out. So please do that. So you just calculate the parallelogram formed by the 3 vectors, and then show that it's 0, and then you're done. Which is sounds easier than it really is, because you really has to calculate that determinant, which is not going to be fun. So I will let you do that as part of your homework. So next, we will look at find some orthogonal vector that goes through some plane. That is, then that you first figure out 2 vectors, and then you figure out the cross product, and that 2 vectors on the plane by subtracting a point from another point, and then you find the cross product of the 2 vectors, and then that's about it. Unless, that's about it. That will be good enough. Okay. So that's example 2.43. Please do that as part of your homework. And next, we're going to do something in physics that is slightly related to what we're talking about. That is the torque. The torque is expressed by the Greek letter tau. I'm on page 180. So the torque in physics, and then don't forget that Greek-looking T is pronounced tau. Okay, it's always good to know how to pronounce Greek letters because it makes you sound very educated. Anyway, measures the force rotating around something, and the tau basically equals R cross F. Now, that means, what does that mean? That actually means at the end is that we're going to do the magnitude, because we don't care that much about anything else. So look at that next example where you're going to calculate that RF sine theta. Remember, the magnitude of the cross product is the the two vectors times magnitudes times sine theta, and you do that, and that's your answer. So please do example 2.44 as part of your homework. So with that, we have come to the end of this section. As you notice, this section, you seem to have to do a lot of examples. That's because the cross product is extremely tedious. It's not exactly difficult, and don't confuse difficult with tedious. Tedious means you have to clean 10 toilets, whereas difficult just means you have to climb Mount Everest. Okay, you can't hardly do it. Tedious, you can do it, but it's going to take forever. But please do the homework patiently and allow maybe double the amount of time that you normally get through a section to get through the cross product. There is also going to be a lot of examples and that you have to do, and also quite a bit of homework. So for homework, please do two problems 185, 89, 189. What is? Give me I can't open that. Okay. 193, 97, 201, 5, 7, 11, 15, 19, 23, 26, 27, 29. At 229, the answer is a little bit wrong, and I will mention it. And when you do the problem, you may also notice there's a slight typo in there. And then finally, 235. And then, yeah. So that is the homework. Please do the homework patiently. And then when you're done, I want to talk about some of them. Now that you are done with homework, let's talk about some of it. 205. We're supposed to prove Lagrange's identity. Now, Lagrange is one of the greatest mathematicians. Of course, nobody's as great as Euler, but Lagrange is still very cool. Now, here's his identity, which we're supposed to prove it. And the way you prove it is you simply plug in everything like you're told. That is, what is u dot v? U dot v is uv cosine theta, right? And then what is u cross v? U cross v is uv sine theta. And then you put the two together, and it does work out. Therefore, one becomes the other or something, and then your proof is done. So that's 205. Next, let's look at 223. All right, 223 says you have to prove an if and only if situation. Oh, I forgot to mention that 223 is also a bit wrong. Let me write that. Now, problem 223, you're supposed to show that u, v, and w are coplanar if and only if they are linear dependent. Now remember what if and only if means. It means both directions have to be proved. You have to do two proofs. One is if they are coplanar, then they are linear dependent. Second, if they are linear dependent, then they are coplanar. And the mistake in here that I found is that it doesn't mention anything about parallel. That is, if they're coplanar, they have to also be parallel, and they also have to be not parallel. No two can be parallel if they're to be linear dependent. If two of them are parallel, then it's not going to work. And I'll show you why that is right now. For example, let's say if u equals to, I, okay? Let's say u equal to I, and then v equals to 2i. So that, and then let's say w equal to j. Now in that case, u, v, and w are coplanar. They're all sitting on the xy plane. There's no c component, right? So they are definitely coplanar. Yet there is no way that you can write w in terms of alpha u plus, what did they say? Alpha u plus beta v. That is not possible because j is going, these things are parallel. They're all going the same direction. There's no way you can combine them with scalar numbers to get them to go in the y direction, in the j direction. It's just not going to happen. That's why the sentence should read, therefore, that u, v, and w are coplanar and non-parallel. No two are parallel. Then they are linear dependent. All right. So having said that, let's do this problem. First, we're going to prove that linear dependent mean proves coplanar. Okay, so here's what we're given. So this is given right now. Given that this is the situation, we have three vectors u, v, and w, such that w is some kind of a scalar combination of u and v, and we're going to prove that this thing is coplanar. Now to do that, we are going to do as one of the examples shows, to prove that three vectors are coplanar, we calculate the parallelepiped, that is the triple scalar product. Okay, because if the three vectors make a parallelepiped that's collapsed, it has volume 0, then it's obviously coplanar. Therefore, so we're going to do that, and that comes out to be, when you do the math, it ends up it ends up like this. See, once you write it out, it ends up you have something like alpha u cross u. Okay, by using the theorems on cross products, and whereas this one over here, you end up beta v cross v, and cross product has the neat property of becoming 0 when things cross themselves. They don't go over well. Okay, so it all collapsed, and therefore it is coplanar. So that part goes pretty nicely. Now the other direction, however, is the part that I was having a problem with. At first I couldn't get it, and then I finally realized the reason is because it isn't true unless you stipulate that at least none two are parallel. Okay, so because if they are, then you can't generate the third one necessarily. So then with the condition that they are not parallel, see, that is none two are parallel, then we're okay. Yeah, in fact, I think if they're parallel, you simply can't do it, because you don't have enough directions, right? Because the two have only one direction, and that thing goes off, the third one goes off a different direction, so you got a big problem. But having said that, however, let's prove the part when they are not parallel. Okay, so nothing's parallel, so this thing is coplanar. We have three vectors that are coplanar, and none two parallel, and we are going to prove that it somehow one vector is going to be equal to the scalar sum of the other two. Now to prove that, we are going to use the vector projection that was taught in the previous section, page 156, where to project something is you use the dot product divided by the magnitude of what you're projecting to. As a result, so we are going to do that and write down the projection. Okay, and I will copy down the equation here. So what we're going to do is that we are given these conditions, they're coplanar, three vectors coplanar, not parallel, and we're going to show that one of the vectors, any one of the vectors is going to be some scalar combination of the other two, alpha and beta being numbers. So what we're going to do is do the projection. This is the projection of w onto u, okay? And that is a number, which we will use it to show that that's alpha. And similarly, this is the projection on v, which is done by the dot product. And this is the projection formula is on page 156. Anyway, so then we did that, and then let's assume there's something left over. Okay, that it isn't just this, there's some other part, and we're going to prove that this part is 0. Now, how are we going to prove that? Now, the projection has already done the dot product, right? So then W3 has this property, that W3 was left over. If you dot it with U, it will be 0, because it comes from we already dotted with U, right? And it's all, we have all here, so there's nothing left. And then similarly, W3 dot V is also 0. And what that means is W3 is perpendicular to U, and W3 is also perpendicular to V, okay? So W3 is perpendicular to U, and W3 is perpendicular to V. And remember, they are all on the same plane. Now, now in Euclidean geometry, if a line is perpendicular to two lines that's not parallel, that line doesn't exist. Okay, so this is called a contradiction, and therefore W3 can only W3 has to be 0. That's the only way this can exist. If it's not 0, then it's a vector that's perpendicular to two non-parallel lines. And that's not possible in Euclidean geometry because right now we're on the same plane here. Okay? And as a result, so being that W3 is 0, then we have proved that W is represented by alpha U plus beta V, where alpha is the projection on U and beta is the projection on V. And that's why it's so very important that U and V cannot be parallel. If they're parallel, then W3 can totally be perpendicular to both lines, right? I mean, if you have two parallel lines, you just, and being perpendicular to both is a piece of cake. If they're not parallel, then it's impossible. It goes from a piece of cake to impossible that quickly. And that concludes our proof for problem 223. So next, I want to do problem 235. 226, you're supposed to prove something by contradiction. So let's do that. Let's say that I plus j plus k equals to some kind of scalar product of just I and j. Okay? Then very quickly you can figure out that k equals to k is some direct representation of I and j, but k dot I is 0, and that's given in the chapter somewhere. And as a result, k dot j is b is also 0. So then you get k equal to 0. Okay, and that's a quick answer. Next, let's look at problem 229. Okay, 229, the answer in the back is slightly wrong. And I will mention that right now in case I forget. See, the exact answer is that the answer at the back says that it's a plus or minus here, but that's not the case. It should be minus match with plus or plus match with minus. See, so if it says plus or minus here, it should say add the minus plus sign on this term. So that's the only mistake. Otherwise, it is correct. So let's look at how to do that. The problem is that we are supposed to find a vector that's orthogonal to some plane, and that plane has the quality of going through containing the entire x-axis and also some point. Okay, so how do we do that? First, we consider a vector that goes from anywhere on the x-axis to that point. Okay, any vector, that is, and the vector that goes from x-axis, a point on the x-axis will be x, 0, 0, right? And going to that point, we'll do subtraction. Like, for example, we'll call Q to be a point on the x-axis, any point. It will call it x, 0, 0, that's a point. And then we'll call U to be the vector from P to Q. P is our original point, the given point, which the PQ then equals x minus 1, 0 minus 2, 0 minus 4, that will be the vector, okay? And so we take the coordinate of Q minus the coordinate of P to get the vector. Then U will be in the plane, right? In the plane that we're talking about, that's the plane that contains both x-axis and P. And then let V be the vector we're looking for, the orthogonal vector, which means V dot U equal to 0 is orthogonal to U for every U. Now, let's write that down. So write that down. We have that equation comes out for all x, okay? Now look at this carefully. Now V1 times some x minus 1 equals to the other stuff. The other stuff is all fixed, okay? I mean, it's V2 and V3, whatever they are, they're fixed. V1 has the quality that it can multiply by any x and still equal to some fixed number. The only way that's possible is if V1 is 0, and then we continue to calculate the relationship between V2 and V3. That's one way to calculate V1. Or another one, you can just choose x equal to 1 and x equal to 2. And because this applies for all x. So then once that's done, then we have the the formula for V is equal to 0 minus V3 and V3, where so now that gives us the direction of V, and now we just need the magnitude to know how the proportion works. So plugging in V, the magnitude of V is 10, and do the formula of the Pythagoras theorem, and we quickly come out as V equals to plus or minus 2 and square root of 5, 2 times square root of 5. And therefore, you have two answers. The reason you have two answers, and they're both correct, is because the orthogonal vector can point up or down, right? It doesn't really say which way to point, so we'll accept both as answers. They are the same, they are equal in value, equal in magnitude, and they just point in the exact opposite direction. So the same thing that's flipped 180 degrees, that sort of thing. All right, so finally, the last problem I want to talk about, 235. You're supposed to calculate the force of some wrench. Well, you multiply it, okay? Plug it into one quick formula of cross product, which is the cross product equals to uv sine theta. And sine theta in this case is 60 degrees, not 30 degrees. Okay, you need to calculate the angle between the vectors, not that other one. So once you figure that out, then it's square root 3 over 2, which is 8.66 foot-pound. And if you're not from the United States and you wonder what the foot-pound is, don't worry about it. A foot in the US is 12 inches. That's why that 12-inch wrench turned into 1 foot. And that's where this answer came in. All right, so maybe someday the United States will get rid of that, the foot-pound, and join the metric system, like they should have done 100 years ago or something. But yeah, for now, you just have to put up with it if you're not from the US. And that marks the end of this section.